Okay, hello everyone. Can you hear me?
Yes.
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 Okay. Welcome to the CPGIS webinar series, GeoAI-driven spatial temporal processes, understanding and forecasting. And so this is the fourth webinar. We have a total of 5. So and next week we have another one. So today we are very lucky to have Dr. Fa Li from University of Wisconsin-Madison. So Dr. Fa Li is a postdoc at the University of Wisconsin-Madison and also a researcher at Lawrence Berkeley National Lab. He will join Stanford University next month, November 2023, and he obtained his Ph.D. degree through the joint Ph.D. program between Wuhan University and Lawrence Berkeley National Lab. His major is remote sensing and GIS, and he is interested in physics-guided machine learning, causality, inference, and Earth system science. He has published 14 articles on top journals in Earth science, including 5 first author articles on journals such as Global Change Biology, Earth's the Future, GMD, CEUS, it's computers environment, urban systems, and also Neurocomputing. And without further ado, let's welcome Dr. Fa Li for his presentation. The title is Understanding and Projecting Wildfire Using Deep Learning. Okay, Dr. Li, I'm handing the floor to you. You are welcome to share your slides.
Can you see your screen?
Yes.
Cool. Cool. Hello, everyone. I'm very happy to give this presentation in CPGIS community. Thanks, Dr. Wu, for the introduction. And thanks, Dr. Yu, Dr. Gao, and Dr. Wu for organizing this webinar. Today, I will present our work on wildfires. Title is Understanding and Projecting Wildfire Using Deep Learning. I'm a postdoc from University of Wisconsin-Madison. This work is a teamwork, so appreciate all the contributions from all the co-authors in the list of publication. I will talk more about this kind of co-authors. I will follow the following outlines for the presentation. First, I will give some introduction or background about wildfires. Then I will introduce our developed wildfire surrogate model of physics-guided machine learning model to improve global wildfire simulation. Then I will introduce the attention fair version 1 model. It developed to make interpretable prediction of tropical wildfires. Then we developed the version 2 to predict large fire probability in the Western US. We may know that the wildfire has strong impacts on humans and Earth, like human property and health, air quality and water quality, tree mortality and ecosystem function, and economic loss. Let me show the next point. Yeah. For the audience, you may also have some experience on this kind of wildfire in your real life. Here I share some of my experience on the wildfires. I still remember the wildfires in 2020 in California. It was an extreme large fire in California. At that time, I live near Berkeley in California. That's my first time to feel the strong impacts of wildfire. I remember it's the 10 a.m. in the morning, and the sky is just like this. And the smoke is everywhere, and also ashes are everywhere on the ground. It's hard to breathe, and actually we buy some air purifiers to remove this kind of wildfire smoke. And 1 may be not enough, and 2 and 3 may also not be enough. Actually, one of my friends bought 4 air purifiers to clean the air in their house. At that time, I have an idea whether I can escape from this kind of wildfires. Maybe I can go to a place with beautiful views, with fresh air. So I decided to go to the Yosemite National Park in California. But when I arrived there, the wildfire have already arrived there. And as the wildfire thermostat welcome you here, and the view like this become the view like this, become a smoky view. So after that, I moved from California to Wisconsin. I thought the Wisconsin wildfire are very rare, so the air quality must be super good. So I feel excited to go to Wisconsin. And after my arrival at Wisconsin, I found that yes, the Wisconsin wildfires are very rare, but the Canadian wildfires are frequent. And the Canadian wildfire emits smokes can be transported to Wisconsin and fully covers Wisconsin. It's still hard to breathe, and it's because of wildfire we spent a smoky summer in this year. So based on this kind of experience, I'm thinking about actually wildfires are not distant from us, or actually from me. It can become a common phenomenon in my real life. So we are wondering whether we can develop some advanced model to better predict this kind of wildfires so that we can know there are some wildfire in advance. Before introducing our work, let's first have a big picture about the spatial and temporal distribution of global burn area or global wildfire. This map shows the global distribution of burn area. From this figure, we can find some wildfire hotspots, like in the Africa, South America, Australia, Southeast Asia, Europe, and North America, and Western US. Over these kind of regions, the wildfire has changed differently during the past 2 decades. And this map shows the burn area trend during the past 2 decades. And the second figure shows the relative trend, which is the trend in figure A divided by the long-term mean of burn area in each grid cell. In these two figures, deeper red color represents increasing trend, and deeper blue color represents decreasing trend, and white color represents insignificant changes. We can find that these kind of wildfire changes are generally spatial heterogeneous. In some regions like Western US, the fires are generally increasing, but in some regions like South America, the fires are generally decreasing. The red figure showed the global burn area changes using 2 different kinds of fire products. One is the G55, the other is the modest fire products. Through this kind of figure, we have found that although these kind of 2 fire products disagree on the fire magnitude, but they both show a decreasing trend at the global scale. A previous study further explored the reasons for this kind of decreasing trend at a global scale. And the conclusion is that it's caused by human, like because of increased human activity, like human suppression effects, caused decreasing trend in burn area. Based on the spatial temporal distribution of wildfire shown in the previous slides, we are trying to answer this kind of 2 questions. It's big questions. We are still working on that. The first one is, at a decadal scale, how future burn area will change. The previous slides showed the burn area decreasing in the historical period, but for the future periods, in addition to this kind of human suppression effects, we also need to consider other factors like climate change. Climate change will make future climate or weather become drier and warmer. It will likely increase more fires. And also this kind of climate change will cause few changes, like fuel moisture changes and fuel availability changes. This kind of fuel condition change will further affect wildfires. So we need to combine all of these factors for future burn area predictions. The other question is how to project this kind of burn area more reliably, especially over this kind of wildfire hotspots. There are different kinds of models to project this kind of wildfires. The first one is the process-based wildfire model. Here, give an example of fire model from an Earth system model or land surface model. Let's focus on the burn area. The burn area is estimated through 2 models. First one is fire occurrence model. It considers factors including ignition sources, human suppression effects, fuel load, or fuel availability, fuel combustibility, or fuel flammability. Based on these kind of factors and also the empirical relationships, the fire occurrence model can estimate the fire counts. After fire occurred, the fire spread model can estimate how the fire spread and the duration of this kind of fire. Based on the estimated information, the burn area can be estimated. And based on this kind of burn area, the post-fire effects can be estimated, like the post-fire effects on tree mortality, the biomass changes, the carbon or nitrogen pool changes, and also fire emitted trace gases like carbon dioxide and methane, and also aerosol emissions. The advantage for this kind of process model is that it's all the relationship between the fire drivers and the fires are physically interpretable. But there are also some limitations or disadvantages for this kind of process model. For example, when we model the relationship between fire drivers and fires, we always assume some empirical relationship. This kind of empirical relationship could be true at some site level or regional scale, but could be not true at the global scale or large spatial scale. Also, we need some parameterization scheme to set this set parameters for this kind of fire process models. This kind of parameterization involves another uncertainty related to parameter uncertainty. Because of this kind of model structure and the parameterization uncertainty, this kind of uncertainty propagates to the model estimate burn area, and the model shows substantial uncertainty across different models. For them, as shown in the red figure, the x-axis is time, the y-axis burn area, and each line represents a R-theta model or land surface model. Through this figure, we can find that the models disagree on this kind of magnitude, interannual variation, and trend of wildfire changes. To narrow down the burn area uncertainty, there are a few ways to go. The first one is that we need to improve this kind of mechanism processes. For them, we need to have a better understanding of the relationship between fire dynamics and fire drivers. Fire dynamics, like including the fire occurrence spread and extinction. And also we need widespread observation to constrain or validate this kind of process model, like observation from ground measures and also from the remote sensing. And finally, we need advanced parameterization scheme to set suitable parameter sets to this kind of process models. This kind of improvement could be easy at a local scale or small scale, but could be challenging at a large scale or at global scale. For example, when we want to parameterize the wildfire at a global scale, it's always consumes a lot of time and includes some computational issue. With the development of AI and remote sensing, we are wondering how to combine AI and remote sensing observation to constrain and parameterize this kind of fire process models so that we can improve wildfire estimations. Based on this kind of problem and problems, we developed a machine learning surrogate model to estimate wildfire at a global scale. It's teamwork. Here, thanks all the contributions from other co-authors, from Lawrence Berkeley National Lab, from Wuhan University, and from UC Irvine and UIUC. For the machine learning surrogate model, there are different kind of strategies. The first one is commonly used one is use a machine learning model, try to learn the relationship within this kind of process model. For the process model, it requires input from parameters and also input of driving factors, and its output fires. And based on the input and output from process models, the machine learning, you try to learning this kind of relationship within this kind of process model. Once this kind of machine learning model can reproduce the projection of wildfire by this kind of process model, we call it a surrogate model. Because as we mentioned before, this kind of process model have substantial uncertainty related to like model structure or parameterization. We further use observation to fine-tune or constrain this kind of machine learning surrogate model. The other modeling strategy is a hybrid surrogate model. For the process models, sometimes not all the processes are unreliable. Some of the processes are actually reliable and have been validated by a lot of observations. For these kinds of reliable processes, we can use the process model directly. But for some unreliable processes, we can build a machine learning surrogate model. And finally, we combine this kind of process model and surrogate model for the final predictions. and also use the observation to fine-tune this kind of surrogate model. Here we use the first modeling strategy to modeling global wildfires. We use the wildfire model from an Earth system model named E3SM. It's a DOE model, and the model includes multiple components, including land, river, ocean, atmosphere, ice, and human Earth interactions. As shown by this red figure, the black line represents the process model estimated burn area at the global scale, and we call this process model as base fire model. We can find that at the global scale, the model generally agree well with these kind of colored observations. The colored lines represent observations from different kind of fire products. But at some regional scale, like in tropical and temperate and boreal regions, this kind of wildfire model shows substantial uncertainty related to these kinds of observations. So we developed this kind of surrogate model to try to improve wildfire estimations at global scale. We use a deep neural network model and use inputs process model and outputs from process model. And inputs include inclination factors, human suppression, field conditions, and climate factors. We use this kind of input and outputs to train this kind of surrogate model, try to let this kind of process model to reproduce the base fire model. We call this kind of surrogate model as DNA fire model. Then we use observation from multi-source observation, including GFAD, fire CCI, and multi-fire dataset and fire atlas dataset to fine-tune this kind of surrogate model so that the model can match better with these kind of observations. In previous publications, it shows that the fire drivers and fire dynamics could be different across different fire regions. So we built a deep neural network surrogate model for each region and combine all the regions for global fire predictions. We compared our model project wildfire with that observation. In this figure, the blue box represents the base fire or process fire project burn area. And the orange bar represents the surrogate model without observation fine-tune. We can find that this surrogate model generally agree well with this kind of process model over different kind of regions. The green bar represents the DNA fire observation with some observation fine-tuned surrogate model, and blue bar the red bar represents the observation. We can find this kind of observation fine-tuned model generally agree well with observations. We also compared our model estimate burn area with observations and other process models along the latitude. The blue line represents our model estimated burn area, and orange line represents model estimated burn area, and the other colored line represents other process models. We can find that our model generally agree well with observations along the latitude. We also compared our model before the 2000 when the observations are relatively rare. The orange line and the black line represent using the charcoal observation estimated burn area, and blue line represents our model estimated burn area. We can find that our model estimated burn area generally falling into this kind of reasonable range and show a slight decreasing trend. Here we give a simple example of how to build a surrogate model to improve the global wildfire simulations by using the process model, AI, and the remote sensing observations. Actually, it's just a simple case in wildfire. There have been other processes beyond this kind of wildfire in the Earth system model. We can also use this kind of modeling strategy to explore other Earth processes. In addition, here we use a deep neural network. It's very simple. And there have been other advanced AI algorithms can be used to explore the Earth system processes. After that work, we developed the attention fire version 1 to predict tropical wildfires. The reason that we select the tropical wildfire is the burn area in tropical area accounts for more than 17% of global burn area. And previous study has shown that climate variable dominated the burn area changes in that area. For them, previous studies show the precipitation changes dominate the fire changes in North and South Africa, and they also show that this kind of dependency, welfare on climate, time lag, nonlinear and spatially heterogeneous. For them, for some grid cells, the wet season precipitation changes show stronger dependency on the dry season wildfire. For some grid cells, the dry season climate dynamics show stronger dependency on the wildfire. So it's important to modeling this kind of time lag, nonlinear and spatially heterogeneous control to predict the tropical wildfires. Based on this kind of fire characteristics, we developed attention fire version 1. It uses the attention maximum to adaptively capture this kind of time lag and spatially heterogeneous controls. Also, thanks all the contribution from the co-authors here. And this figure showed more details about the attention fire model. We considered input factors here, including ignition factors, suppression effects, fuel conditions, and climate conditions. We organize these kind of factors as time series and input into the gates of LLTM and transform this kind of information as hidden state dimension, hidden state vector for different variables at different time steps. Then we use temporal attention to adaptively capture the time lags controlled on wildfires. Based on this kind of time lags control, we use a variable attention to adaptively capture more important variables in different grid cells. Here, give an example how this kind of attention maximum works. For some grid cells, if wet season climate variable shows stronger impacts on dry season wildfire, then the attention maximum will assign larger weight to this kind of wet season climate. And for some grid cells, if human dominates this kind of grid cell, the attention maximum will assign larger weight to this kind of human factors. And for some grid cell, climate dominates this kind of welfare dynamics, the attention maximum will assign larger weight to this kind of climate variables. We use the following data sets and variables to train and validate our attention fire model, including welfare data sets from GFAD, climate data set from NSAP, including variables, precipitation, temperature, pressure, humidity, short wave radiation, wind speed, and vapor pressure deficits. And also we consider fuel conditions, including fuel moisture and wood biomass, vegetation biomass, and litter biomass. And also consider human activity proxied by population density, road density, and livestock density. And we also consider land cover information and the ocean index. The reason for using this kind of ocean index is that we want to use the teleconnections between ocean to land to predict the wildfire with some time in advance. We use our attention fire model to predict the burn area in the 3 tropical regions. The first column, 3 maps, shows the observed burn area across the 3 regions, and second column shows the model predict burn area. Through this kind of comparison, we can find the model predict burn area generally agree well with this kind of observations. Also, although in some regions like South America, the burn area generally underestimated the observation. Then we compared our model performance with other machine learning models that have been commonly used in fire studies. This figure shows the performance comparison. The axis shows the different models. The blue box is our model, and the y-axis shows the model bias represented as mean absolute error. Through this kind of comparison, we can find that our model generally performs better than the other process models or machine learning models with lower bias. For the welfare studies, accuracy is important, but accuracy is not only thing we care about. We also care about the model interpretability. We need to make sure the model is interpretable rather than overfitting. So after that, we quantify dominant drivers across 3 regions. This figure shows the variable importance in 3 regions. From this figure, we can find VPD or vapor pressure deficit dominant welfare in North Africa. When the VPD is larger, it means the climate is drier and when the VPT is lower, it means the climate is wetter. And we found that precipitation dominant wildfire in the two regions. These kinds of findings were consistent with the previous studies and suggest that climate wetness conditions dominate tropical wildfire dynamics. We also show the spatial dependency of wildfires on this kind of dominant drivers across three regions. In these three maps, a deeper red color represents stronger dependency, and light red color represents weaker dependency. Through this kind of comparison, we can find the dependency generally spatially heterogeneous. In some grid cell, it's weak, and in some grid cell, it's stronger. We've then compared the dependency of large fires on these kind of dominant drivers against that of small fires. As red line represents the dependency strength of large fires and a blue line represents dependency strength for the small fires, we can find that the large fires dependency is significantly stronger than that of small fires. We also showed the variable importance in different months for predicting fires in this fire season. For them here, give an example for predicting fire in November. The factors in variable importance in October, September, October, August is shown here. And deeper red color represents stronger dependency. Through this kind of map, we can find the climate variable in October is more important for predicting fire in November. And through the heat map here, we can find that for the North Africa wildfires, the on-site or dry season or on-site or fire season climate variable are more important for predicting fire in the fire season. But through this heat maps of here, we find that for the South Africa and South America, the climate importance shows some time lags, like for predicting fires in the fire season, the variable in wet season and also wet to dry season show stronger dependency. This kind of time lag control actually are the basis for some sub-seasonal to seasonal fire predictions, and our model just capture this kind of information for predicting wildfires in advance. Based on this kind of model, we are wondering how future burn area or wildfire will change in these three regions. We consider factors including future land use changes, population growth, project climate, and field conditions from 5 fully coupled Earth system model in CMIP6 under different future greenhouse gas emission scenarios to project the burn area changes in the three regions. The first column 3 figure shows the burn area changes as the grid style scale. The deeper blue color represents decreasing trend, and deeper red color represents increasing trend. From this kind of figure, we can find the changes in burn area generally spatial heterogeneous in this Africa region, but in the South America region, the burn area generally increased over this kind of area. The red column 3 figure shows the total burn area changes in the three regions. The blue line represents the historical changes of burn area. We can find that the burn area generally decreasing in North Africa, increasing in South Africa, and increasing in South America. We project the future burn area changes as shown by this red line. We found that the burn area generally decreasing in North Africa and the fire change become much weaker in the South Africa and become increasing in the South America. The reason for increasing wildfire in the South America is that we know that Amazon forest is located here. The Amazon forest is not fuel limited, and the climate change in the future will make the weather here become drier and warmer. It will likely increase more wildfires, so it causes increase in wildfire in the future. We quantify the impacts of the dominant driver changes on this kind of future fire changes by removing the trend in the dominant climate variables and reproject the wildfires as shown by this black dashed line. It's a project of wildfires after removing the trend in the dominant climate drivers. We found that after removing the trend in dominant climate variables, the trend in burn area generally disappear. This kind of results suggest the importance of climate change in this kind of dominant climate variables on the future burn area changes. We also compared our model estimated burn area changes with that under different future scenario. The red line is a high greenhouse gas emission scenario, SLP 585, and the light blue line represents a low greenhouse gas emission scenario, SLP 126. We can find that under low greenhouse gas emission scenario, the trend generally become much weaker. This kind of results suggest importance of greenhouse gas emissions and future development pathways on future burn area changes in these three regions. After the attention fair version 1, we now are working on attention fair version 2 to make a projection of wildfire in the Western US. The reason that we are interested in Western US is that let's see the first two maps. This map shows the fire events before the 2000. Each point is a fire event, and larger point size represent a larger burn area. And this map shows the fire events in the recent 2 decades. Through this kind of comparison, we can find that the fire events have become more widespread and larger in the US. And most of the wildfires are distributed in the Western US. And the following figure shows the burn area changes over the past 4 decades, as shown by these red bars, and also show the changes of VPD or vapor pressure deficits across these kind of 4 decades. We can find that when the VPD increases or the climate becomes drier and warmer, the burn area generally increases. This kind of increase in wildfire not only shows some negative impacts on ecosystem, but also it could be hard for the insurance company to manage this kind of wildfire risk. So, supported by the insurance company named American Family Insurance, we developed attention fair version 2. Here, thanks the co-authors from Madison, Lawrence Berkeley National Lab, and scientists from American Family Insurance. Thanks Fujiang, Qing, Kunxiaojia, Aridan, Peng, Volker, and Min. Compared to the version 1, the version 2 have some changes, mainly trying to improve the interpretability because the insurance company more was interested about this kind of interpretability. They want to make sure these kind of fair predictions are reliable rather than overfitting. We here can explicitly consider the positive controls of fuel availability on the large fire probability, and also explicitly consider the negative impacts of human suppression on the large fire probability. We also use attention mechanism to capture the complex relationship between fuel flammability and large fire probability. This kind of modeling strategy is a kind of a hybrid modeling strategy. And the advantage of this kind of modeling strategy is that we can understand the wildfires from 3 dimensions: the fuel, from limitations of fuel availability, fuel flammability, and also human suppression. We use the following data sources and variables to build this kind of wildfire model, including the climate weather variables, VPD, precipitation, surface temperature, air humidity, wind speed, and potential evaporation transpiration. And also we consider fuel moisture and fire danger index listed here. And also we consider the topography information, elevation aspect and slope, and also fuel availability. We consider fire dates from the agency reported fire dates and also the satellite observed data sites. We also consider other information, including land cover and population distribution. we compared our model with a physical process-based model. It's the United States National Fire Danger Rating System. And this kind of process model uses the surface weather conditions from temperature, humidity, precipitation, and solar radiation to estimate the live and dead fuel moisture. And also use the wind speed to estimate the danger of fire spread. And finally, output two index used for forecasting wildfire. One is the burn index, the other is energy release component. These kind of two index have been widely used in US to forecast wildfire risk. We also compared our model with some machine learning-based model, including some tree-based model like random forest, XGBoost, decision tree, and also we compared our model with some neural network-based methods. We use two evaluation metrics to evaluate the model performance. First one is F1 score. It's a balance between precision and recall rate. When the F1 score is larger, it means the model performance is better on classifying the small and large fires. And when the AUC score is larger, it means the model performance is better. This figure shows the model performance comparison using two different evaluation metrics. The first one is the F1 score. The x-axis shows different models. And through this kind of comparison, we can find that generally this kind of random forest model and attention fire model perform better than the other machine learning model or process models. And attention fire model performs slightly better than the kind of random forest model. But in terms of AUC score, also these kind of two models perform better than the other model, but the random forest model performs slightly better than attention fire. Again, as we mentioned before, for the wildfire prediction, accuracy in point high accuracy is good, but it's not good enough. We also need to make sure our fire prediction is physically interpretable rather than some overfitting. Here, give an example of fire like prediction from the kind of black box models. For example, the black box model make a projection of no fire danger or low fire danger in a gray cell. The problem is how can we trust this kind of predictions? Right, we need at least to know the reason why this kind of black box model to predict this kind of low fire danger or no fire danger. For them, through some transparent explainable AI or XAI, we can know that it's because the temperature is low, the VPD is low, the fuel is not enough. Because this kind of reasons, the model projects no fire danger or low fire danger, and this kind of reason are also physically interpretable, right? Actually, there have been different kinds of explainable AI or XAI been developed to explain this kind of black box machine learning models, including some gradient-based methods and also some perturbation-based methods. In gradient-based methods like integrated gradients that we have been commonly used in interpreting some neural network-based models, and also some Shapley value-based methods like the Shapley value sampling. This kind of Shapley value can not only tell us the contribution from each factor to the large fire probability, it can also tell us whether this kind of factor positively or negatively contribute to the large fire probability. So using these kinds of XAI, we try to evaluate the physical interpretability for different machine learning models. Here, give an example of how we evaluate the model interpretability. Use XAI, we derive dependency between temperature and large fire probability. We can find that there is a general positive relationship between temperature and large fire probability. This kind of positive relationship generally follows the physical knowledge, right? When all the other factors are the same, increase in temperature will cause an increase in large fire probability. But for this kind of random forest model, it does not follow this kind of physical rule. It shows when the temperature increase, the large fire probability first increase, then decrease. This kind of relationship is less interpretable. And we use the XAI to evaluate relation between each factor and large fire probability for different machine learning models. The bottom row shows the physical knowledge, and the plus represents the positive relationship. For them, increase in this kind of burn index will cause increase in large fire probability. And for example, and this minus represents a negative relationship. For example, increase in fuel moisture will cause a decrease in large fire probability, and also increase in precipitation will cause a decrease in large fire probability. And we identified whether this kind of machine learning model correctly captures this kind of relationship. Here, Y represents the model correctly capture this kind of relationship, and N represents the model incorrectly capture this kind of relationship. And through this kind of comparison, we can find that the attention fire model generally capture more physical relationships than the other machine learning models. Based on this kind of results, we evaluate the model performance through 2 dimensions. The first one is accuracy in like F1 score. Second one is interpretability, like the percentage of correctly captured relationship. And through this comparison, we can find that our attention fire model generally perform better than this kind of this kind of machine learning model with higher accuracy and higher interpretability. Although our attention fire model performed worse than this kind of process model in terms of interpretability, but our model showed substantially higher performance than this kind of process model. In addition to this kind of accuracy and interpretability evaluation, we also tested our model whether it can capture some large fire or extreme large fires or some mega fires. We trained our model using data before 2018 and test the model using data in 2019 and 2020. This figure shows the burn area changes across different years. And we can see that 2020 is a large fire year, and 2019 is a small fire year. And the red map shows the model project large fire probability in 2020. As we can see, this kind of black boundary shows actually occurred fires. We can find that this kind of boundary generally overlapped well with these kind of red regions. It means the actually occurred fire generally have some stronger large fire probability. And also we found that our model failed to capture some wildfires like in this region. So we are still working on trying to improve our model. And also through this kind of map, we can find that the large fire probability shows substantial seasonal variation. In the winter or wet season, the fire probability is lower, but in the summer or dry season, the fire probability is larger. We predict the top 5 largest fire in 2020 using our model with 1 month in advance. This figure shows the predict large fire probability in 2020. As we can see, the largest fires occurred generally overlapped with red regions with large fire probability. And also, this figure shows the anomaly of large fire probability. When it's red, it means the large fire probability is larger than the large fire than that in the same period of the other years, like the multi-year average. And this figure shows that the boundary of the wildfires generally overlaps with the red regions, except this fire is just partially overlapped with this kind of red region. We compared the model estimate large fire probability for the largest fires in different years. The red line represents large fire probability in 2020. It's a large fire year, so the probability is significantly larger than the other years. And this blue line represents large fire probability in 2019. It's small fire year, so the large fire probability is smaller than the multi-year average, as shown by this light blue line, and also smaller than the large fire year 2020. Also for this kind of years, large fire year in 2020 also showed the large fire probability, except this one. as we discussed before, the fire boundary just partially overlaps with the red regions. We also use XAI to quantify the dominant drivers for each fire events. We found that these three variables, although the order will change, but these three variables generally dominate the wildfire for the top 5 largest fires. Let's conclude the presentation. First, I present our model, wildfire surrogate model. It's used process model, AI, and remote sensing to improve global wildfire simulations. Then I introduced the attention fire model. We developed to adaptively capture the time lag and spatial heterogeneous control for predicting tropical wildfire. Then we developed the attention fire version 2 and integrate with XAI to evaluate the model performance and the interpretability. We found that this kind of machine learning model or deep learning models can perform reasonably well, but with wrong relationships. So in addition to the model performance, we also need to care more about this kind of model interpretability. Before the end, I'd like to put an advertisement in our lab at University of Madison. Our lab at University of Madison, our MEANS lab at University of Madison, is looking for fully funded Ph.D. students and postdoc. Min is an excellent advisor, expert in earth science, expert in remote sensing, and expert in land surface modeling and AI. And our group have wonderful atmosphere. Our group members are experts in different areas, including remote sensing, GIS, and earth science, and also computer science. So we are happy to collaborate with each other, and we are happy to welcome you join. And actually, welfare is an important part in our research. In addition to welfare, we also interested in other processes, including greenhouse gas emissions and climate change, remote sensing theory and its applications, GIS, like advanced GIS algorithm like GeoAI, and land surface energy, water, and carbon cycles. We use a bunch of AI, Earth system model, and causality inference to project and understand these kind of Earth processes. In addition, we use the integrated assessment model to explore the human-Earth interactions. For them, we use this kind of model to quantify the impacts of climate change on our human social economics, water, and energy sectors. We have publication in lots of top journals in earth science. If you are interested in our research or if you are interested in our group, please feel free to reach out. You can directly contact me through the email, or you can contact us, our group members. If we are interested, we will offer you an interview opportunity. That's it. Thanks everyone for your time and attention. If you have any question, you can ask or put your question in the chat. We can discuss this kind of question one by one. Thanks.
Okay, thank you, Dr. Lee, for the great presentation. There are a lot of information to digest, and so now it's time for questions. You can type in the chat, or you are welcome to unmute yourself if you have any questions.
Hi. Dr. Lee.
Hi, Yuchi.
Thanks for the presentation. It's very informative. And I have two questions. First one is that because I'm not familiar with wildfires, but I think if one area is burned in this year, it has very low probability to be burned in the next year. So I'm wondering whether your model has considered about the historical information about the burned areas or not. Another question is that since your model is for the, I say it's study the whole USA, I'm not sure. Have you ever tested the generalizability of this model? Like I think maybe different areas may have different environments and causing domain shifts, which may lower the model's performance in some certain areas. Thanks.
Thanks, Yushi, for the question. That's two great questions. First one, the question is, if the grid cell there have occurred fire, there is low fire probability to reoccur again. Yeah, that's the truth. And for our fire model, like our welfare surrogate model, we focus on the global welfare at a large spatial scale. Like for example, the spatial resolution for this kind of grid cell is like 1 degree or 2 degree. For this kind of larger grid cell, if the fire occurred in this kind of grid cell, it will reoccur in this kind of grid cell because the spatial coverage is large, right? So we do not explicitly consider this kind of fire reoccurrence with a low fire probability within the same grid cell. So yeah, and for the Western US, we focus on spatial resolution of 1 kilometer. It's not our model outputs is not burn area. It's a large fire probability. We just focus on the large fire probability occurred if there is an ignition. So we also do not explicitly consider this kind of fire recurrence. And for the model generability validation, actually we have validated our model using different kind of validation scheme. Like we validated across space. For example, we train the model in a space and validate the model in another space. And also we use this kind of temporal cross validation. Like we train the model in a specific time period. Then we validate the model performance in another time period to validate this kind of model performance. Also, we use the random cross validation, just randomly select like 80% of data set for model training and the other data set for model testing. And also, your question is great. We currently we haven't applied our model like the attention fire version 1 to other regions, like in China, in India. We haven't applied this kind of model to the other regions. And so our attention fire version 1, we just focus on the tropical wildfire. So we haven't put this kind of model in other regions. Yeah. So do I answer a question?
Yes, well answered. Thank you so much.
Thank you.
Okay, next question from Jerry. For ML surrogate model, where to get parameters?
Oh, yeah, that's a great question. Actually, in our machine learning surrogate model at a global scale, we do not consider this kind of parameters. We just consider the input of driving factors and the output of burn area. Use this kind of information to train this kind of machine learning model, because we assume that for the process model, we actually set a suite of parameters for this kind of process model. And based on its input and output, the machine learning model can learn this kind of complex relationship within this kind of process model. But also because we do not consider this parameter, so the parameter uncertainty could be propagated to our surrogate model. So we further calibrate this kind of surrogate model using the observation to fine tune this kind of surrogate model. Yeah.
Okay, thank you. Next question is from Adumu Bala. Great to see international audience here. And he asked like what type of opportunities are available in your lab, resource collaboration, postdoc, internship. Maybe you can show your last slide again, that you show some of those. And email, I think it's at the beginning of your slide, but we can send it later.
Yeah, let me share my screen. Yeah.
Any other question?
Yes.
Anyone want to unmute yourself?
That's my email. If you are interested, you can contact me or contact me.
Maybe you can copy just your email and then paste into the chat.
Yeah. Yeah.
Anyone else?
So Dr. Lee, I have two questions. So the first question is related to your seasonal or sub-seasonal forecast of either the tropical wildfire occurrence or wildfire probability, and the second is the US wildfire probability. So both of them are longer term, right? So it's they're monthly. It's mostly monthly, right?
Yeah.
So when you do monthly or sub-seasonal predictions, what's your thinking comparing to more short-term predictions? Like how difficult can these two different types of models be? And would you like in the future to try out some short-term predictions? That's my first question. Maybe I can ask my second question later.
Yeah. So yeah, we have developed the wildfire prediction model and across different temperature scale. Here just presents the fire prediction at a monthly scale. For the insurance company, they focus on the long-term fire prediction because they have more time to change their decisions or policies to make more money. So here presents the long-term fire prediction. Actually, we have developed fire prediction at daily scale and also weekly scale. Of course, based on my opinion, this kind of short-term prediction is much easier than the kind of long-term wildfire prediction. The long-term depends on the time lag control or temporal or autocorrelation is kind of input variables, and also based on some teleconnections, like from ocean to atmosphere and then to precipitation change in the land. This kind of processes will like take about from 1 month to several months. Based on this kind of time lag information, we can predict wildfires from monthly to seasonal scale. There have been also different studies to predict wildfire only using this kind of ocean index to predict the fire from seasonal scale to even 12 months later. Yeah.
Thanks. So following up on that, the insurance example, you were showing the fire probability, like the burn index or the burn probability, right?
Yeah.
There are many red grid cells.
Yeah.
So my question is that because you want to, well, how do I frame the question? So maybe the accuracy is more towards on your capability of predicting fire probability and less so than not predicting fire. Do you understand that type of logic? So we want to focus on accurately predicting the positive probability of fire instead of making both classes accurate. Is that true in your case?
I know your case. You mean it needs to predict actual large fire probability and also you need a balance between with no fire, right?
Yes.
Yeah, that's a
Thank
great
you.
question. Yeah, that's a great question. Actually, we have discussed about this kind of question. For this kind of decision makers, actually, there are so many grid cells are right with large burn area, a large probability. How they can believe this kind of prediction or make some specific policies. So yeah, actually our model balances the small fire probability and the large fire probability. And we evaluate this kind of performance using the F1 score, which a balance between accuracy and recall using this kind of metrics. But also our model predicts a red region with large burn area, large fire probabilities, too many grid cells, right? So next time we are trying to integrate this kind of large fire probability with some ignition sources. Like we have some ignition sources distributed like in some parks, near some parks or a road network. We can use this kind of ignition sources to further focus on this kind of grid cell with some ignition sources.
Great,
Yeah.
thank you. So,
yeah, thank you.
My second question is like, what is your thinking of the feedback loop from your interpretable deep learning going back to the modeling community, because you use a lot of process-based models. What is the usual way that you're going to do, or you are probably already doing that?
You mean how to use the interpretable AI or ask AI in more general area, right?
And in terms of giving feedback to process-based models.
Oh, yeah. That's an interesting question. Actually, we have done some XAI or causality inference to infer the causal relationship or interpretable relationship from some observations. And based on this kind of observation-based relationship, we can, for example, give an example to evaluate whether the model overestimates a specific relationship or underestimates a specific relationship compared to observation. then if the model underestimates this kind of process, we will do some parameterization or change the model structure to further improve the importance of this kind of processes. But yeah, we are still doing this kind of work, and there are some feedbacks, but not too many. Yeah.
Okay, great. Thank you.
Yeah, thank you.
Thank you. Any more questions? I have one question. So for the model, how do you like take into consideration some of the human factors? Because like wildfire, natural environment factors, they are certainly very important, but sometimes it's just simply human cause the wildfire, because especially if there's any firewall or some other human cause wildfire, how do they, I mean, the model take into the account?
Yeah, that's a great question. Currently, for the process model, it considers human effects through this kind of population density and also some GDP, this kind of factors. This kind of factor. For the machine learning model, actually, it considers more factors like power line, road network, the livestock density, and some WUI, welfare urban interface, and this kind of information. But actually, this kind of human factor is not enough. Not enough for actually predict this kind of welfares. Also, actually, we have discussed with Dr. Gao about this kind of how to integrate human mobility with this kind of welfare prediction. Because we know, like for some people go to the welfare, go to the park, it will increase the fire probability. It will create ignition sources. So we are thinking about how to integrate this kind of human mobility with this kind of welfare.
I was wondering if there's a, I mean, for the current wildfire database, do they have some kind of attribute showing that it's a natural fire or like human caused fire? So if that is the case, I mean, you can generally estimate, right, in every year in general, I mean, in the US, how many fire are caused by natural factors or how many are contributed by human factors? And also the other follow-up question would be, in terms of doing the probability validation, I think it's always important to think about the spatial and also the temporal frequency, or the basically how long do you predict that into maybe the next year, or people are going to say, okay, the stock market is going to crash. Yeah, it's always true. It's going to be like, are you talking about within a month, within a year, within 10 years, right? It's correct. And so I think it's the same mechanism applying here. So when you if you predict the probability, I think it's important to take that into account. Like, are you predicting like the wildfire probability within this year, within this month, within this season? And how do we actually eventually validate this? Because now we already have a longer time scale and also a lot of wildfire. I'm not sure if there's any work that has done to actually, for example, use the wildfire data from 2010 to 2020, something like that, and then train your model, whatever. And can those probability model, I mean, align with the wildfire really happen between, for example, 2020 to 2023? So if there's like very consistent, they align with each other, I mean, that means the model perform very well. But sometimes it's not always the case, because you can predict a lot more, have a lot of like false positive, because it doesn't actually happen. Just my random thoughts is that it's important to consider the temporal aspect of these models. You don't have to answer, just like some of my thoughts. The last one is how to turn this into operational, right? Especially the last couple big wildfire, for example, in Hawaii, in Maui, right?
Yeah.
It's important not just predict the probability, but when something happens, sometimes, for example, how do you deal with something that's not within like the model that can predict at all? But I think it's would be very useful if something happens. How do we predict how it's going, right? So now we have more, for example, the ghost data set. geostationary operational environmental satellites. So those like providing data every minute, every 5 minutes or every 10 minutes. But it's very costly solution. But I think those data are quite important if you really want to predict how it's going, right? So we predict that it's going to, in general, this is going to happen, but predict how it's really going in real time. I think it's also another very important topic that might be very useful because it really saves money and people's life if you can really turn that something into operation, right? And my model predict is, and if it happens, depends on wind speed, depends on the land cover, whatever, right? Also the population, where should people evacuate?
Yeah.
I think FEMA would be very interested in your work and also insurance companies, because I heard that some companies are no longer operating in California because
that's correct.
many wildfire, the risk is just too high. So now they don't make any money, right? So if using a model there, this is too high, we're moving out of the business, then yeah, but you want to make sure that it's high accuracy and actually can validate that it's actually true. Yeah, this is just some of my random thoughts, and we are over time. And last question for PhD remote sensing: what is the target department for faculty position? This kind of general question. So it's
that's general. You can
we're
answer.
talking about like geography. You can some like environmental science. There are also some like data science program or environmental science, geography. Yeah, it varies. Also, for example, natural resources. So it depends on the university. So, or you can just look at, for example, in CPGIS, go to the list of CPGIS members and see where those members are working at. So you can in general get a good idea about if you get to a major in remote sensing and GIS, where do you like find a job? And also go to AAG, right? The job posting at AAG. So most of the relevant one will be there. Some also in geology, some might be in atmospheric sciences, some might be in natural sciences, natural resources, geography, urban planning. It varies. Okay, so I think that's all for the questions, and thank you once again, Dr. Lee, for the great presentation, and thank you everyone for attending. And next week, next Thursday, same time, we have the final presentation. So looking forward to seeing you again. And you are welcome to follow the CPGIS or Weixin Gongzheng Hub for updates. And we will upload the recording to YouTube and Bizan by tomorrow. So if you miss some of those, you can rewatch at your convenience. Okay, thank you everyone, and have a great night and or great rest of your day. See you next time.
Thanks, everyone.
Thank you, Dr. Lee.
Thank you.
Mm-hmm.